So last time I gave a formal definition of what's called worst case. Here's n, and here's TA of n. This is the number. This is the worst case number of operations that algorithm A does on input of size n. And we said that was some kind of curve, which is the max. Okay. So this was WAN, which was worst case number of ops as a function of n. Okay? And that's what we did last time, basically finished that formal definition. There's a handout on the class website, or you can go look at the video, again, if you're a little unclear about that. And then I said, well, we'd like to find this exactly for particular algorithms A, when we're talking about particular algorithm for some particular problem. We'd like to know this curve exactly, or this function exactly, but we're rarely that lucky or that good. And so we want to estimate it or approximate it, usually from above, but sometimes from below. And so we would like to have a function like that, where f of n is always greater than or equal to WA of n, but we're usually not that lucky or that good either. And so usually the best we can do is some kind of function that isn't always above WA of n initially, but usually gets to be above it later on. Now the usually, well, I'll say something about that. But this is sort of the rough picture of what we're going to be able to achieve. And this is an upper bound on WAN. On WA of n. Okay, now we want some language to talk about this kind of relationship between two functions. Function where eventually one grows bigger than the other, sort of, and I'm going to have to tell you what the sort of means, but not necessarily initially. There can be some kind of funny stuff like this initially. And the common notation for that kind of relationship between two functions is the Big O notation. And I'm sure everybody here has seen Big O notation in some earlier class, but I want to give you at least a semi-formal definition of it. The book actually has a more rigorous and complete definition. But we want to say two functions, f of n is Big O of another function, g of n. So two functions, f of n and g of n, if the ratio, if the limit of the ratio as n goes to infinity, f of n over g of n, if that limit goes either to a constant greater than or equal to, greater than 0, okay, f of n, g of n. No, I don't want that. Uh-oh, I'm going to have to think. What I wrote here is unclear, so I'm going to have to engage my brain, which is always dangerous in front of people, and even worse when there's a camera here. Okay, so f is on top, g is on the bottom, and we want f to be dominated. Essentially, the intuitive thing is f is dominated by g. Okay, so we're looking like that. So if I take the ratio here, what kind of thing happens? Well, g could get to be huge relative to f, right? And if that happens, then what does this ratio go to? 0, good. Or it could happen that, well, they're just pretty much mirroring each other. They're parallel like that. Something roughly like that. Okay? And then what happens to this ratio? It goes to some constant, okay? And just for emphasis, we'll say this. We'll write this constant as less than infinity. Well, I mean, I don't know whether you think of infinity as a constant or not, but just in case you do, we'll say the constant is less than infinity. And by the way, for the video, this is the end of the board here, not this mark. Okay, so I didn't drift over. Okay, and what's excluded from here? What couldn't happen in this ratio? Because we're looking for G being essentially bigger than F. So what possibility is not listed here? Less than 1? This doesn't say it. This still allows the possibility of being less than 1. Okay. What other possibility is not listed here? We don't have infinity. Okay. This ratio shouldn't go to infinity. If it went to infinity, that means that F would really be growing much faster and bigger than G. But this notation is to say that G bounds F. F does not grow faster than G. So essentially, intuitively, F of n grows no faster than G of n. And this intuitively is roughly. Okay, so this is a not a complete definition, but it is certainly a correct statement. F of n is big O of G of n if, when you take the limit of this ratio, you either get a 0 or you get a constant less than infinity. So let me give you some examples. Okay, F of n equal to 5n squared, and G of n 25n squared. Okay? So if you take the ratio of I do want F here, but why is this? This is definitely growing bigger. Well, all right, let's just plot on. 5n squared over 25n squared. The n squared's, 1/5. Yeah, okay, sorry, I don't know why I was getting panicked there. F is about 1/5 of G, and that's fine. But the point is that they're proportional to each other, and we're getting this constant of proportionality, which is 1/5. So we get a C, and that's less than infinity, so that satisfies this definition here. Okay, now what happens, however, if we do 25 and 5? Then F is bigger, certainly F is bigger than G, right? It's growing bigger than G. So we wanted intuitively that F grows no faster than G, but it seems that if you take the formal definition here, if you take the limit of the ratio, what do you get? You get 5, okay? Well, 5 is a constant less than infinity, so we've satisfied this definition. The limit of the ratio of F and G goes to this constant 5, which is less than infinity. And so that says that 25n squared is big O of 5n squared. And yet, 25n squared is actually bigger, is always bigger than 5n squared. So what can we conclude from this? Well, what we conclude is this is right, but this is why I have intuitively or roughly is only in quotes. Okay? Because there is still the possibility that F actually grows faster than G. It's just that they grow proportional to each other in this way. And so that's the level of detail that's as precise a statement as we wish to make about the relationship between F and G. We're not going to be paying attention to the constants in front of these two functions. We're really paying attention to what's the dominant growth characteristics of these two functions. What characterizes the growth of these two functions is the n squared, is the square in the exponent of the n. And the constant that's in front of here, it's just not in the level of detail that we're going to care about when we look at particular algorithms. Because the number of operations that a particular algorithm can do is influenced by all kinds of small issues in the algorithm or on what particular computer you run it in. And that's a level of detail that we're not concerned about in this class. So this definition is perfectly fine for the relationship of two functions. F is big O of g if the limit of the ratio goes to 0 or c, even if you get something, even if you're looking at two functions like that. Okay? All right, so that's why I say roughly or intuitively, g grows faster, or f grows no faster than g. It looks like that. Okay. Well, we're also interested in talking about the converse side, or the inverse side of that, which is, here again, this is W-A-N, which is the function we're mostly interested in. Okay, so that's really our f of n is that. And we're interested in making statements that, intuitive statements of the following, roughly f of n grows at least as fast as g of n. Okay? So we want to, the rough picture here is that we have some function g such that f grows at least as fast as g. Well, okay. First of all, the notation, f of n is equal to omega g of n. Instead of using big O, we use this term omega. And that happens if the limit, as n goes to infinity, again we're going to look at f of n over g of n. Let's think about this one. F of n is growing at least as fast. Well, it could really dominate. F of n could grow much, much faster than g of n. And if that happens, what would this limit converge to? Infinity, definitely. F of n, if it really blows up relative to g, that could be infinity. Okay? That's one possibility. What's another possibility? Well, f grows faster than g, but again, sort of proportionally, let's say. Okay, they kind of mirror each other. In which case, what does the limit go to? Some constant. And one thing we know about that constant, it's greater than what? Well, no, greater than 0. Yeah, it won't be a constant equal to 0, because a constant equal to 0 would mean that g was growing very fast relative to f. Okay? And we don't have that. So here we have these two different possibilities. F of n is said to be omega of g of n if this limit of the ratio either goes to infinity or goes to some constant greater than 0. Okay, now let me point out, in both of these cases, we have here the limit. We're talking about what's happening when n goes to infinity. So even though I drew this picture here where g is always bigger than f, you can have any kind of behavior going on at the beginning, because this is only talking about what happens as n goes to infinity. So for small n, any sort of thing is possible. And then again, because of this phenomenon we were talking about, you don't necessarily have g strictly bigger than f. It can actually go down below. Okay, but it has to go below then in a way that was proportional to f if that happens. Okay, and the same thing is true over here. G is not necessarily strictly less than f. It can do all kinds of wild things initially, and then even later on, g could be bigger than f, but if it does that, it would only be proportional to f. We have this possibility here of going to a constant greater than 0. Okay, so that's another piece of notation that we'll use. Mostly we're going to use big O. Occasionally we'll use omega. And we're actually going to use fairly frequently another notation. F of n is theta of g of n if f of n is big O of g of n, and f of n is omega of g of n. Okay, so it's possible that f of n has both of these relationships to g of n, big O and omega. So remember, roughly, big O says that f of n grows no faster than g of n, and omega says roughly f of n grows at least as fast as g of n. Of course, both of those are rough statements. This is the exact statement for omega. That's the exact statement for big O. But what would it mean intuitively if function f grows no faster than g and grows at least as fast as g? Does that sound like a contradiction, or just what's the resolution of those two statements? Somebody's got to talk besides me here.
It grows the same.
It grows what?
It grows the same.
Yeah, they grow roughly the same. Okay, so f of n and g of n grow roughly the same. And what does that mean formally in terms of the limit as n goes to infinity of this ratio, f of n over g of n? What does that ratio go to? Not necessarily 1, but what? Some constant, yeah, some constant. And what do we know about that constant? Yeah, bigger than 0 and less than infinity. So basically you can see that what's happening in theta, it's the intersection of the possibilities, really, or when you have this case and when you have this case. Okay, so and basically it says, well, f and g are growing proportional to each other. Which one is actually the bigger and which is the smaller? That's not specified in the theta notation. They're just they grow proportional to each other, some constant there, greater than 0 and less than infinity. Okay, so if I tell you that two functions, well, let me give you just an example here. We've seen this before. Okay, f of n is big O of g of n, right? And if you plug in those particular functions there, you would also see that f of n is omega of g of n, right? So f of n and g of n are theta of each other. One's 25n squared, one's 5n squared. They grow proportional to each other. The constant of proportionality, if you have f divided by g, is 5, and so it's converging to a constant. And that's what this says, is that it's a constant between 0 and infinity. So they're theta of each other. All right, now if I have two functions, and I tell you that one is theta of the other, is that more or less information than if I tell you that one is big O of another? Which one is the more precise statement? If I say f of n is theta of g of n, or if I say f of n is big O of g of n? Theta is what? Yeah, theta is more precise. Theta is when you have more information, you've deduced more about the relationship of f and g. Okay, so if I say, if I know that f is theta of g of n, and somebody says, oh, f is big O of g of n, is that correct? Yes, it's correct. It's just not as informative. Okay? So if somebody just says, oh, f is big O of g, when I know that f is theta of g, what they're saying is correct, it's just not as informative as what I know. On the other hand, if what I know is that f of n is big O of g of n and somebody else says it's theta, they're making a stronger statement which may or may not be true. Okay, then I would have to actually evaluate it and see. Okay. All right, and I could ask you all kinds of other combinations like that. Sounds like very good midterm type questions. There is a mistake that people often make, which is that when they should be using omega, they use big O instead. It's very common. So you can often see a statement like this, even among professional computer scientists who should know better. I see this in publications, and it's one of my pet peeves when I see people say that. They say something like, f of n grows at least as fast as big O of g of n, where these are two particular functions. Okay? So f of n, let's say, it's a function we're interested in. And they'll say, well, this grows at least as fast as big O of 5n cubed. Okay? Well, if you just think about this in terms of the rough intuitive things, when f of n is big O of 5n cubed, it means roughly that f of n grows no faster than that. Okay? So this is saying f of n grows at least as fast as some function which grows no faster than 5n cubed. So what are you really saying about f of n?
Are you saying it's theta? It's an upper bound.
It's what?
Upper bound.
It's, which is an upper bound? F of n is what?
The upper bound.
Of this one?
Yeah.
Okay. Well, I'm saying 5n, if I interpret that one that way, f of n grows at least as fast. Okay, it's growing at least as fast as some function, call this g of n, some function g of n, where all we know about g of n is that it grows no faster than 5n cubed. So you should be able to see that f of n could be anything. If f of n is less than 5n cubed, that works out for here. If f of n is bigger than 5n cubed, that works out for here. My conclusion is this says nothing about f of n. This is completely empty, vacuous, meaningless, no good sentence. Okay? Nonsensical sentence. So what they wanted to say, probably, is that f of n grows at least as fast as omega, a function that grows no faster than, that grows at least as fast as 5n cubed. Okay, and that we could then conclude that f of n is also omega 5n cubed. Okay, this is clearly a really small point that one of my pet peeves. So if you're not getting it, what I'm just saying now, and you want to look back on the video and think about it more slowly, the conclusion here should be if you go through the actual definitions of what big O of n is, and then try to plug it into this statement, you'll see that that puts no constraints on f of n, what f of n is. So this is just vacuously saying nothing about f of n. Okay. Any last questions about these notations? Mostly we'll use big N, big O, and we'll use theta when we know enough to be that precise. Omega will come up occasionally, but it's just mostly big O and theta. All right, so now I want to start looking at some actual algorithms and doing some actual analysis. And the kind of algorithms that we're going to be looking at are divide and conquer, and analysis by recurrence relations. Okay. So I said earlier that this class is about both analysis and design, or design and analysis. That teaching design is difficult. Teaching analysis is much simpler and more straightforward. We have tools of analysis we can actually teach. But there is a class of algorithms where design, there's a basic design paradigm that can be taught, and you can look for it when it's successful. And those are algorithms that are divide and conquer type algorithms. Those are algorithms which, just pictorially, in terms of a cartoon, here's some instance of a problem, and let's just take, again, to be concrete, sorting n numbers. So this is the problem, sorting n numbers. And the divide and conquer paradigm would say, let's try to break up this instance of the problem, or any given instance of the problem. An instance is a list of numbers. Break up the instance of that problem into some smaller instances, maybe 2 smaller instances, maybe more than 2. But that's the dividing. And then you're going to solve the 2 or more, I'll just show this as 2 for the moment, 2 or more instances. You're going to solve those Okay, solve those 2 separate or 2 or more separate instances of the problem of sorting this set of numbers and this set of numbers. And then with the solutions to those 2 problems, you solve the whole instance by using, at any rate, the 2 or more small solutions. And this is what's called the conquering, I guess, part of this. This paradigm probably would have been better to say divide and reassemble, or divide and use, or something like that. Divide, conquer, and reassemble. But this is just called divide and conquer. All right, who's seen an algorithm of this type? Okay, which one is it?
Merge sort.
Okay, merge sort. Any other ones? Okay, merge sort. That's a good example. That's really sort of the classic example of this kind of algorithm, and we're going to do an analysis of that in a minute. And we'll see 3 or 4 other algorithms of that type. And the divide and conquer really does show up enough to be called a paradigm, and to learn it and to look for instances, look for problems that can be solved by that general approach. It's definitely worth knowing. And then the analysis of the running time of the divide and conquer is going to be done by setting up recurrence relations and solving those recurrence relations. That's something that you may not have seen, and that's definitely a central element of this part of the course, is learning how to do that. Okay, so let's look at merge sort. Now, the book does merge sort. Initially, in the first chapter, it talks a little bit about merge sort, but then it really doesn't do the analysis until chapter 5. So I think it's sections 5.1, 5.2, something around there, maybe up to 5.3. You can take a look. They do merge sort and then the analysis of it. But it's sort of odd that the book doesn't have anywhere, even at the beginning or here, a really clean statement of what merge sort is. I guess they just assume you've seen it somewhere. But let's write it down so we know exactly what we're talking about. So merge sort of a set, let's say L. So L is a list of numbers, and merge sort is going to be the algorithm that takes the list of numbers and produces a sorted order of them. Okay, so initially, we can look at a base case. If L is equal to 1, then we're just going to return L. Okay, if the list only has one element, it's already sorted. You don't have to do anything with it. Otherwise, divide L into two lists, L1 and L2. Of roughly the same size. N over 2. Okay, now let me say a little bit about the level of precision in this class. You can divide L into two lists of exactly the same size, N over 2, when N is what? Even, exactly, thank you. But you can't when N is odd. Okay? But I'm not going to write that down here. I'm just going to say roughly the same size. And you will know what that means. If you were going to program this, you'd translate it into something more precise. Maybe, you'd pay attention to whether N is even or odd or something like that. But in terms of the high-level description, there are lots of little details that we don't need to pay attention to. And you just have to get some sort of intuitive sense of when a detail is important and when it isn't. Okay, we could divide L into two lists, L1 and L2, roughly the same size. How are we going to divide them, by the way? Is there some particular rule we want to use? Those of you who remember merge sort? Well, it turns out you can divide them arbitrarily. There's no particular rule that's telling you which is going into one list and which is going to L1 and which is going into L2. Okay, just arbitrarily. And then, so this is the division. This is the conquering or the solving separately. We're going to merge sort L1. Okay? How do you merge sort L1? I mean, here we are describing what merge sort of L is, and in the middle of it I'm saying merge sort L1. So what's the magic word? Recursion. Yeah, this is a recursive algorithm. So we're going to merge sort L1, and we're going to merge sort L2. Okay, both of these calls are recursive. And then another function which I haven't described yet is to merge. We're going to merge the result of merge sorting L1 with the result of merge sorting L2. Okay, so this is another function which I have to define. And then what I do with this is I return it. Okay? These things are really annoying because they video a square at a time, and I don't ever know whether they want this square or this square. Anyway, it's too bad they have these. Okay, so you return the merge of having merge sort L1 and merge sort L2, two recursive calls, and then you do the merge. Okay, well, let's look at this function merge. So you merge two sorted lists, L1 and L, well, here I was saying it's the merge sort of L1 and merge sort. Let's just make this arbitrary. Let's say it's a list called N1 and a list called N2, okay? Where N1 is sorted and N2 is sorted. Okay? So merge is a function that takes in two sorted lists and returns, it produces a sorted list of N1 union N2. So the union of those two sets, or two lists, is the sorted list of those two lists taken together, that's what this function should produce. Okay? So I'm going to write this down not in pseudocode, but just sort of in English. And here's what it does. It successively compares the first element of N1 with the first element of N2 and removes the min, removes and outputs the min in that compare. Okay, let me do an example of that. Let's say we have two lists of length 3, of 3 elements each. Here's N1, N2. Okay, maybe this is 3, 5, 7. Maybe this is 2, 4. I'll make this a 6, 5. Okay, so two lists, two sorted lists, 3, 6, 7, 2, 4, 5. They're both sorted, both length 3. I want to create a sorted list of the union of these. So this says successively compare the first element of N1 with the first element of N2, and it removes and outputs the min of that compare. So it compares these two, okay, 3 compared to 2. The min of that is 2. So it removes that and outputs 2. Then this is the first element now of N1, and this is the first element of N2. After you do a removal, you have a new first element or top element.
It's new indexes.
It's what?
Sorry, new indexes.
New index?
Yes.
I'm not sure what that...
Do not worry. I just mean that the indexes for the N2 sequence has already changed.
Yeah, okay. Okay, so what was said is correct. It's what you're suggesting is more pseudo-type code that you would go into here if you were going to turn this description into a program. You would want to have an index that's pointing to the top, and then when you remove and make a new top, you'd change your index to point to here. That's absolutely true. And that's the kind of description I didn't want to get into, because then I'm writing code or pseudocode. Yeah, but you're right that that's exactly what it means. Okay, so now the algorithm would compare 3 to 2 to 4. Okay, and now the min is 3, so that gets output, and this gets removed. And now this is the first. It remains the first element of N2, but 6 is the new element of N1. And so those two are compared, and the min now is 4. That's output. And now 6 is compared to 5. Okay, now 5 is the min. It's output. Okay, and now now we have a case that we didn't include in here. 6, the list 6, 7 is remaining, but this list is empty. So N2 is empty. So at this point, we can just output what remains, 6, 7. Okay? So I could put in here the additional thing. If N1 or N2 becomes empty, output the remainder in order of the remaining list. It's N2, it's N1 or N2. Okay, so that's exactly what happened in this case. N2 became empty, and then we can output the remainder, 6, 7, of the remaining list, which is N1. Okay, so at this point I ask, does everybody understand sort of the general, in sort of general sense, how merge works? We just have this level of description, successfully compare the first element of N1 with N2, and remove and output the min of that comparison. And then we have this additional, the addendum here, which said if one of these two lists becomes empty, then output in order the remainder of the other list. Okay? So that's what merge does. So I'm going to leave it to you to convince yourself that merge is correct. We always, in the algorithm, you're looking at algorithms, first want to know that the algorithm is correct. Does it actually take in two ordered lists and that are sorted and produce a sorted list of their union? Okay? If I wanted to prove that formally, by the way, how would I do that? What's a good general approach to proving that formally? Now, I know from last spring when I asked that question, there was somebody in the class, always the same person, who said, why would you need a proof? It's just obvious. You know, of course it's correct. You tell me why it's wrong, but that's not a proof. A proof is not where you go up to somebody and say, tell me why it's wrong. If you can't tell me why it's wrong, that's my proof. No. What would be a strategy for getting a formal proof of this? Yeah?
You would assume that the algorithm is incorrect and then work out a contradiction?
Yes, that's possible. That's possible. You could assume it's incorrect and then find some contradiction. I'm not sure what the details would be, but I certainly wouldn't want to discourage you from trying that. There is a more natural, sort of obvious answer. Yeah. Proof by induction, right. So induction goes hand in hand with recursion, goes hand in hand with divide and conquer. All of these kinds of techniques are very interrelated with each other. So you would induct on the size of these lists. If two lists, for example, were both of size 1, okay, then you can just say, well, by construction. When you say in a proof by construction or observation or something, it means this is so obvious, I'm not going to say anything more about it. Okay? If the two lists are each of length 1, then it is really obvious that when you compare them and output the min, that's the smallest of the two, and then what's remaining, that one list becomes empty and you output the remainder, that's the bigger of the two, and therefore you have a sorted list. So when the two lists are of the same size, then, and so on. And then you can make the inductive assumption that this algorithm is correct when two lists, well, you probably want to, because in the algorithm they can become of uneven size, you would want to say something like, when the largest of the two lists is k, then the algorithm is correct. And then you do the inductive step, which is when the largest of the two lists is k plus 1, okay, one larger, then, or when maybe probably you want to say when the sum of the two lists is k plus 1, something like that, you have to prove that the algorithm is correct. Well, what's the proof of that? So we've assumed that the algorithm is correct when the sum of the two lists is k. And now we're looking at an instance of the problem where the sum of the two lists is k plus 1. Okay? And we want to prove that the algorithm does the right thing based on the assumption that it always does the right thing if the sum of the two lists is at most k. Well, you look at the details of the algorithm. The two lists are assumed to be sorted, so certainly the smallest over the entire set of elements here, the smallest of the union is either the smallest of N1 or the smallest of N2. That's definitely true. You compare them explicitly and output the smaller of the two, so definitely you're outputting the smallest of the union, right? So the algorithm is right at that moment. Its first output is the smallest element in the entire union of those elements. At that point, you have two lists They started out having total size k plus 1, but now you've output 1, so now they have size k. And what you're doing next is the same algorithm as merging those two particular lists. But those two particular lists have size at most k total. So now you can apply the induction hypothesis, which says that the algorithm will do the right thing. It actually sorts and outputs the elements in sorted order. And therefore, the whole operation of the algorithm is in sorted order. Well, this isn't a class on induction. I'm sure everybody has studied some induction and used some induction, but if you're a little rusty on that, you should take a look at the handout that I have on the class website about induction. But induction, so I didn't write this down here in class, the argument I just went through verbally, but hopefully everybody saw what's involved in a formal proof. Okay. Now, I only have a couple of minutes left, but I don't want to stop here. I want to at least make one more step in this whole analysis, or maybe two more steps. So here we have merge, okay? And now that we know what merge is, and we know how to merge, because we've seen the details over here, you have to ask, is this algorithm for merge sort correct? So recursively, it merge sorts these two lists. It divides L into two lists, L1 and L2, roughly equal size. Recursively merge sorts these, so these are now sorted. It then applies merge, which we just argued will take two sorted lists and produce a sorted list of the whole. So does this algorithm correctly sort L? Yes or no? Yes, thank you. Yes, it does. Modulo, the little programming details of when maybe n is odd or even or whatever. But basically, this is correct. And if you wanted to do a formal proof of it, what's the magic word? You could do a formal proof of this by induction. All right, so proof of correctness. All right, now we want to ask, how many operations does it do? Well, first of all, what's the primitive operation in this algorithm? Last time I said, whenever you want to do an analysis of an algorithm, you have to decide what the primitive operation is. What's the primitive operation in this particular algorithm? Is what? Comparison, yeah, it's done over here. That's actually the real work is done when you compare two elements at a time. That's where the real work of the algorithm is done. And so we want to count the number of comparisons that are done. And last little thing, how many comparisons? Think about this for next time. I claim that the number of comparisons, the worst case number of comparisons that are done when you merge two lists whose total length is n, the worst case number of comparisons is n minus 1. So think about that for next time, and we'll pick it up from there. Okay, I'll be around for the next half hour here if you want to stay around for questions about homework or anything, or I'll talk a little bit about stable marriage, which is a problem on your homework.